In today's video, I want to show how to use an oscilloscope. An oscilloscope is a voltage measuring device. So you can measure a voltage that is changing with time. Typically, we use a voltmeter sometimes to measure the voltage, but a voltmeter cannot show us the changes that are happening to the voltage waveform. If the voltage that we are trying to measure is changing with time rapidly, and we are interested in seeing how the waveform is changing in time, then the only way we can visualize that is using an oscilloscope. Therefore, an oscilloscope is a very useful device, and it is important to understand how to use it properly. As such, an oscilloscope is a very useful device when we are trying to debug a circuit, or if we are trying to understand what's happening at different points in our circuit. So as I said, the oscilloscope measures the voltage, and to measure the voltage, we have these probes. So this is one probe, and you can see we have these two terminals. The black one is called the ground, and the other terminal is the positive terminal. So the voltage between these two terminals is the voltage that will be displayed on the screen here. So we will see the voltage on the screen as a function of time, and the probe will be connected to the circuit where we want to measure the voltage. So any voltage that is between these 2 points will be displayed on the screen, and we will be able to see the time dynamics of this waveform. The probe on the other side is a BNC connector, as you can see here. This is a BNC connector, and we can just connect it to one of the two channels of the oscilloscope. I have a two-channel oscilloscope, as you can see, channel 1 and channel 2. So this means I can see two different voltage waveforms at the same time as a function of time simultaneously. Right now, I have turned on only channel number 1. If I want to see both of the channels, then I can turn on channel 2 as well, and then I will be able to see both of the waveforms at the same time. For now, I'm only interested in channel 1, so therefore I will turn off channel 2. The menu over here, we can either leave it or we can remove it. So this way we can see a little bit wider screen. The screen of the oscilloscope, on the horizontal axis, we have time. So you see that the horizontal axis is divided into a number of segments. For instance, in this case, for my oscilloscope, I have 1, 2, 3, 12 divisions along the x-axis, and I have 8 divisions along the y-axis. So x-axis is the time, and y-axis is the voltage. The knob over here, which says volts per division, it controls the voltage per division. So for example, currently I have channel 1, as you can see here, it is 1 volt per division. So this means that each division represents 1 volt, and because I have 8 divisions, so therefore from the bottom of the screen to the top, I can have a voltage 8 volts between the two terminals, between the 2 points of the probe. So I can show 8 volts on this screen. We can change this voltage per division. For example, right now it's 2 volts per division, 5 volts per division, and so on. And you can see that the maximum I can do is 5 volts per division. I can decrease it to the minimum, and the minimum is, as you can see, 2 millivolts, so which is 0.002 volts. So the minimum is 2 millivolts per division. So each division will now represent 2 millivolts. Similarly, we have the same knob for channel 2, and right now channel 2 is 1 volt per division. I will bring this back to 1 volt per division. Next to the volt per division, you see this line, which is a straight line and then a dashed line. This actually shows us what kind of coupling we are using. To explain the coupling, if you press the channel button, it will bring this menu, and you see on the top here, it says coupling. And the coupling, we have a straight line and a dashed line. This means this is called a DC coupling. So we have two different options for coupling. One is called the DC coupling, or if I want to change it, then the other one is called the AC coupling. The AC coupling is represented by this sine wave. And you can see if I use AC coupling, this waveform over here will change too. By DC coupling, we mean that the voltage is shown on the screen the way it is, both the DC component and the AC component. However, when we use AC coupling, then the DC component is removed from the waveform that is displayed. So for example, if I have a voltage waveform where I have a sine wave, let's say, of 1 volt peak to peak, but that sine wave is offset at, let's say, 10 volts DC. So this means the maximum is 11 volts and the minimum is 9 volts. So I have a sine wave which is riding on top of a DC voltage. So sometimes we are not interested in the DC part because that is something which is constant with time and it doesn't give us any more information. And we are more interested in the time variation of the voltage waveform. So therefore, we want to get rid of the DC part. And if we want to get rid of the DC part, then we can use this AC coupling, which will remove the DC part and only show us the AC component of the voltage waveform. If you press it one more time, it will show this ground symbol. And this means that now the voltage on the probe will not be displayed, just the ground, which is 0 volts. So the 0 volts will be displayed on the screen. The other option, the other menu item is the invert. So I can either say invert is off or I can invert on. So what this will do is that it will just invert the waveform. If you want to invert the waveform, you can use this option. The third one is bandwidth limit. Sometimes if there is a noise on your signal and you want to remove that high frequency noise, then you can turn on the bandwidth limit. For my oscilloscope, this is a 60 megahertz oscilloscope. If I turn on the bandwidth limit, it will pass the input signal through a low-pass filter, which has a cutoff frequency of 20 megahertz. So all those frequency components that are above 20 megahertz will be removed. So this will kind of make the signal a little less noisy. The final option is the probe multiplying factor. Here it is 1. You can use 10 or 100. So for example, now I have a probe multiplied by 100, and you see my original volts per division was 1 volt, but if I use this, it will show that this is 100 volts. So this is just a multiplying factor, and we will discuss that shortly. I will keep it at 1 for now. Now, the probe here, most of the probes have this switch over here, which says multiply by 1 or multiply by 10. So you can change the position of the switch, and this is used to measure high voltages. So currently I'm using it at multiply by 1, so x1. So this means whatever the voltage is, the probe will just measure that voltage the way it is without multiplying by anything. But if I use the multiply by 10, then what the probe will do is that it will divide the voltage by a factor of 10 and show me on the screen. So then when I'm reading that voltage, I will multiply that by 10 over here. Let's say I want to measure 100 volts. 100 volts is a large voltage. Now to measure a large voltage, I will use the maximum volts per division, and which is 5 volts per division. So this means that each division is 5 volt, and because I have 8 divisions, the maximum I can display on the screen is 5 times 8, which is 40 volts. So I cannot show 100 volts on the screen. So to be able to see 100 volts on the screen, what I will do is that I will use this switch and bring it to the multiply by 10 position. So now the 100 volts will be divided by 10, and 10 volts will be displayed on the screen. So using the 5 volts per division, I can see that the waveform will take 2 divisions. So the 2 divisions will come to this point, and we can easily see that. However, on the screen, it will look like that I'm measuring 5 plus 5, I'm measuring 10 volts. But we have divided it by 10 using the probe. So the actual voltage, for us to read the voltage, what we can do is that we can use this factor over here just to let us know that we have actually divided the voltage by 10 using the probe. So therefore, we will multiply by 10 over here. And now each division is 50 volt instead of 5 volts. So the 2 divisions will represent 100 volts, which is the correct voltage that we are measuring. All right, so let's bring it back to 1 and remove this menu. So we have this volts per division. Now, channel 1 is represented by yellow color, as you can see over here. I can move the position of this curve up and down using this vertical position, using this knob. I can bring it up and down, and it is sometimes useful, as you can see, because if I want to see 2 different waveforms and I want to separate them from each other, then I can move them up and down. So this is the vertical position, which is useful. you can move your waveform to any position you want. Uh, Typically, I would keep it in the center. We have the same options for channel 2. So we have volts per division, and we can set the vertical position of the of the trace. The next item is the knob, which is called the time per division. So this knob will control how many seconds or milliseconds per division we want to display. Currently, I have, as you can see, 10 milliseconds. So each division along the x-axis is representing 10 milliseconds. We can change it to any value we like. So for example, if I bring it to maximum, it's 10 seconds. So now each division is 10 seconds, and it will take the curve, the waveform, 10 seconds to cross one division. And that's a very long time. And you can see I have 12 segments or divisions, so it will be 120 seconds for me to get one trace. So that's the maximum time per division that we can have, and the minimum in this case is, as you can see, 1 nanosecond. 1 nanosecond is 10 to the minus 9 second. It's a very, very small period of time. We can also move the trace horizontally using this knob, as you can see. And we will show that when we look at a voltage waveform, that we can move it left and right so that we can focus or we can zoom in on a certain part of the waveform. Let us see a typical sinusoidal waveform using the function generator, and we can display it on the oscilloscope, and then we can explore the different features of the oscilloscope. So for that, I will turn on the function generator. I have selected a sinusoid waveform, and these are the probes of my function generator, and I will connect this to the oscilloscope. So I will connect the negative to the negative, and I will connect the positive of the function generator to the positive of the oscilloscope. And now you can see that I already see a waveform on the scope, but it is not very clear what is happening. So the first thing I think we should do is that I have used a multiply by 10. So which means that I'm dividing the signal from the function generator by 10, and then I'm displaying it on the screen. So it looks very small. So I will bring it back to multiply by 1. And now you can see that this is the actual waveform that the function generator is producing, which is a little bit too large. It is going out of the screen. So what I can do is that I will make it 2 volts per division. And now you can see that each division is 2 volts. So it's a sinusoid waveform. And you see I have one division, two divisions. So I have two divisions below the zero line. And you can see this is the zero line. This arrow represents the reference, the ground, the 0 volts. So I have negative 4 volts, and I have positive 4 volts. You see 2 plus 2, 4. So this function generator is actually producing 4 volt peak, or we can also say this is producing 8 volt peak to peak. So peak to peak is 8 volts. And you can see that we have 4 divisions for that, 2 plus 2 division, 2 plus 2 divisions. So that 4 divisions, which represents 8 volts peak to peak. So that's the voltage that the function generator is producing. Now, I want to see what is the frequency of this sinusoid. Right now, we are actually seeing less than 1 cycle. So I will use the time division. So right now we have 5 milliseconds, and I cannot see the whole 1 cycle. So what we should do is that we should increase this time. And now I have 10 milliseconds per division. So now you can see that we can now, about 2 cycles we can see. To measure the frequency of this signal, I need to measure its time period. Okay. So a time period is the time that the signal that the waveform takes, where it will then repeat itself. So we can choose any 2 points. So for example, we can choose the peak point. So from this peak to the second peak, that's 1 time period. Or we can choose the minimum voltage to the next minimum, that is one time period. Or we can choose, for example, this 0 point to this 0 point. That's also 1 period. So any 2 points on the waveform after which the waveform repeats itself is called the time period. So I can see that here I'm crossing 0, and here I'm crossing 0 again. And I have like 1, 2, 3, 4, 5, 6, about 6 divisions. So the time period is about 6 divisions, and each division is 10 milliseconds. So total of 60 milliseconds. That's the time period, 60 milliseconds. So if the time period is 60 milliseconds, then the frequency will be 1 divided by 60 milliseconds, which is equal to 16.6 hertz. So this means that this waveform has about 16 cycles in 1 second. So that's the frequency. So you can see that we can measure the voltage amplitude, and we can measure the frequency or the time period of the signal using an oscilloscope by measuring the divisions. Another way to measure these quantities is to use the built-in function, which is called measure. And if you press this measure over here, you can choose what you want to display. So for example, currently I'm displaying the peak-to-peak voltage. For channel 1, it is 7.9 volts, and channel 2 is off. The maximum is about 3.8 volts. Channel 2 is off. Frequency is about 16 hertz. This is what we calculated. Period is about 62 milliseconds, and we thought it was approximately 60 milliseconds. And the average value is almost zero because it's a sinusoidal waveform, and the average value of a sinusoid is zero because the positive area and the negative area are equal. So therefore, the average value is zero. So you can measure it using this way, or you can measure, or you can just make an estimate by looking at the divisions that you have. To remove the menu, I can just remove it, and then we have this waveform back. Now let's see what the vertical position will do. So I can move this waveform down, for example. So now this is my reference point. So this represents 0 volts. So I have 2 divisions above and 2 divisions below. So I can move the waveform up and down, and using the horizontal position, I can move the waveform left and right. As you can see, we can move it left and right, and the location is actually indicated by this arrow over here. And for most of the time, we would like to keep it in the center. All right, and I will put the vertical position in the center as well. Now this is a sinusoidal signal at about 16 hertz. Now let's say if I increase the frequency using the function generator. So for example, if I change the frequency from 16 to, let's say, by a factor of 10 more, so now it should be 160 hertz, 160 hertz, and now we see too many cycles on the screen, and it is a little bit too crowded. So what we can do is that we can change our time division, and now you can see that each division is 2.5 millisecond, and we can find the frequency again of the signal. You can press measure again. So you can press measure, and the frequency is now 159, which is almost 160 hertz as we expected. And also the amplitude remains the same because we did not change the amplitude. Now, if I change the amplitude using the function generator, for example, I decrease the amplitude, or I can increase the amplitude. So the results can be seen on the oscilloscope. Now this voltage is too large for my screen to show, and right now it's 2 volts per division, so I can make it 5 volts per division. And now you see I have about 12 volts above and 12 volts below, so it's about 24 volts peak to peak. I will decrease the amplitude back to about, let's say, 10 volts peak to peak. So I have about 10 volts peak to peak, and I can bring it to 2 over here, and then add some offset. So let's measure the voltage peak to peak, and peak to peak voltage is about 10 volts, as you can see. So now I have a 10 volt peak to peak signal. The average value is almost zero, and you can see it on the scope. Now I want to show the effects of the coupling, DC coupling, AC coupling, and ground. So let me press channel 1. Right now the coupling is DC. Right? So what it means is that we are actually seeing the waveform the way it is without any modifications. We are not removing any part of the waveform. The function generator gives us the option to add an offset. So for example, if I add an offset to this signal, I can have this waveform, let's say 5 volts per division, and let me remove this. So you see now this is the function, this is the voltage that the function generator is producing. I have a sinusoidal, but this time it is riding on a DC level, and the DC level is somewhere over here, as you can see. So So the signal remains positive for all the time. It never goes below zero, because zero is over here, as you can see by this arrow, channel 1. This is the zero. So the signal doesn't go negative. It is always positive. It's a sinusoid which is riding on a DC. And this is what a DC coupling will show me. It will show both the DC part and the AC part. If I'm not interested in the DC part and I want to remove that part, then what we can do is that we can press channel 1 again and go to the coupling and make it AC. So you can now see here that this is AC coupled. And now you see what the probe has done, that it has removed the DC part from the signal and it shows me only the AC part, which is the part that is changing with time. So the AC coupling can remove the DC part of the signal that you want to see. I will go back to the DC coupling. This is the original waveform. The third option is ground. So the ground is just that the probe is actually not going to show you anything. It will just, the scope will show you the ground level. And it is useful so that you can adjust your ground properly. The position is 0.00. So that's for the ground and DC coupled. I will remove this for now. Now I want to get rid of the DC components of the offset, so I will bring the waveform back to the original position. We saw inversion. If I want to invert the signal, so then I can press this option over here, and now you see the signal is inverted. Or if I don't want to invert it, I can turn it off. It is very important to understand how the trigger works for an oscilloscope. The trigger stabilizes the waveform on the screen, and it does it by plotting one trace on top of the previous trace. To explain this, let us consider that we have the screen of the oscilloscope, and the horizontal axis is the time axis, and as we have seen that we have 12 divisions along the time axis on my oscilloscope. So let's say I have selected the time per division to be equal to 1 millisecond. If this is the time that I have selected using the time per division knob, so this will mean that on the horizontal axis, I will have a total of 12 milliseconds. Okay, so this is the amount of time that will be displayed on the horizontal axis. Now consider that I have connected a sinusoidal signal to the probe of the oscilloscope, and that signal has a time period of 6 milliseconds. Okay, 6 milliseconds. So this is half. So you see we have, let's say this is our 0 point. This would be 6 milliseconds, and here we have 12 milliseconds along the x-axis. So the time period is 6 milliseconds. Therefore, I should be able to see a waveform that looks like this. Right? So I will see two complete cycles of the sine wave, because my time period is 6 milliseconds and I have 12 milliseconds. So within 12 milliseconds, we should be able to see two complete sine waves. And after that, after the second sine wave has been plotted, the waveform will come back to the starting point, and then it will continue plotting. And you can see that the second trace will fall on the previous trace in this case, and we will be able to see a stationary waveform on the screen. By the way, the frequency of this signal would be 1 divided by 6 milli, which is 1000 divided by 6, and that is equal to 166 hertz. So in this case, we were very lucky, and the reason was that our frequency, or our time period, was an integer multiple of the total time along the x-axis, which is very rare, which will not happen most of the time. Most of the time, we will have a frequency or a time period which will not be an integer multiple of our total time period of the scope. What I mean by this is that let's consider a different frequency. So again, this is my screen of the scope, and this is the center line. Now, instead of having a time period of 6 milliseconds, let's say my waveform has a time period of 5 milliseconds. So 5 milliseconds. So this is my 0 point, and this is, I have 12 milliseconds over here. using the same time per division. Time per division is 1 millisecond. So let's say I have 10 milliseconds over here and maybe 5 milliseconds over here. So this means I have one sine wave in this 5 milliseconds, and then I have another one cycle in the next 5 milliseconds, and then I have 2 milliseconds left. Correct? I have 2 milliseconds left, and in this 2 milliseconds, the sine wave will, let's say, come to this point. Now, at this point, the signal, the sine signal, will not stop, and it will actually be doing something like this with the same time period. All right, so let me draw this. So the input signal would be doing something like this. Now, the oscilloscope will now start tracing this part, the one that I have plotted with dashed line. So it will start tracing it over here. So we will see a sine wave that does something like this. And then it ends here. So now the oscilloscope will come back to the starting point and it will start tracing for here. And we can see that every time we will see a different trace, the starting point will be different. So therefore, it will be a mess and we will not be able to see a stationary waveform. We will not be able to measure the time period or the details of the waveform very easily. So to avoid this issue, the oscilloscope provides us with a trigger option. So now let's see how the trigger can help us to get rid of this problem. So again, this is my screen of the scope. I will assume the same thing, that time per division is 1 millisecond, and I have a time period of the input signal to be 5 millisecond, 5 millisecond as before. Let's say this is the point where I have 10 millisecond. The end, of course, is 12 millisecond, and the beginning is 0 seconds. Now 10 divided into 2. So I should see one period over here, and then another period over here, and then the waveform will increase, and then the waveform will continue doing this, as we said last time. And this is the 0 reference. So if I have selected using my trigger menu, right? So if we go to the trigger menu on the scope, and if I say that I'm going to use a trigger level of 0 volts, and edge is rising, right? So what I mean is that we will see on the scope that we can control the trigger level by what voltage do we want the scope to trigger, and we can control the edge, rising edge or the falling edge. So let's say I choose trigger level to be 0. So what it means is that when the scope comes to this point, the end, the scope will not start plotting this part on the screen again. The scope will wait for the trigger condition to happen. And the trigger condition is that the voltage level has to be equal to 0 volts and the edge should be rising. That is my trigger condition. If both of those conditions are met, then the scope will start plotting. Okay. So now let's see, where can we see that those conditions are met? If you follow this waveform, the voltage is not 0. The voltage is 0 here. Right? So the voltage is 0 here, but this is not the rising edge. This is the falling edge because you see the waveform is decreasing. So the scope will not trigger here. The scope will wait and it will wait until this point. So the voltage is 0 here, and this is the rising edge, right? This is the rising edge. So it will trigger at this point. So when the scope triggers, the scope will start plotting from here. And this waveform will be plotted on the screen again, and you can see that it's this point, and it will be plotted like this on top of the previous curve. And when we come here, the scope will wait again. It will not plot until this time. And when this time comes, the scope will start plotting again. And this way, we can have one trace on top of the other trace. And therefore, we would be able to see a stationary waveform on the screen. Now, the trigger level, we have selected it to be 0 volts. You can set it to anything. the trigger level knob, you can rotate it, and you will see that there will be an arrow on the right side, and this actually tells the oscilloscope what is the trigger level. You can bring it up and down, and that will control the trigger level. You can also control the edge. You can make it a rising edge or a falling edge. So now let's see how this can be done on the scope. As we discussed earlier, the trigger will enable us to plot one trace on top of the previous trace so that we can see the waveform stationary, so the waveform is not moving around. Now the trigger is shown over here, and this knob actually will help us to move the trigger level to any voltage that we want. So up and down, we can change the trigger level, and this will give us the menu items for the trigger. So for example, if I click this, these are my trigger options. Right now, it says that the trigger type is edge. So what it means is that the way the oscilloscope will look for a rising edge or a falling edge of the voltage waveform to trigger uh, the trace, which will start plotting the trace. The source of the trigger is currently channel 1. As you can see, this arrow over here is the trigger level. So when the voltage of the waveform approaches this level, then the oscilloscope will start plotting. And you can see here that the oscilloscope starts plotting here. So this level determines what will be the waveform, which will be at the intersection of this arrow and this arrow, right? So for example, if I change this voltage level, let me increase it. And now you can see the starting point is here, which is a larger voltage. And if I bring the arrow down, which is the trigger level, the starting point is actually decreasing. And if I bring this arrow all the way to the 0 point, then you see this waveform will start at 0. Okay, so this is the trigger level, which actually tells the waveform when to start plotting. So it will start plotting from the center, half here, and then half here. And then then the oscilloscope will wait for the next trigger to happen, and then it will start plotting again. So the next trace will fall on the previous trace, and we will be able to see a stationary waveform. So the source is channel 1. So the waveform of channel 1 actually causes the trigger to happen. Now let's see, my channel 2 is not connected to anything. So if I say that the source is channel 2, so now you see the waveform is not able to trigger. So the waveform will not be stable, it will keep on moving. And the trigger level, if I bring it up or down, it's not going to do anything. And you can see the waveform is not stable. The other options for the source are external. So if you want to have an external source, then you have to connect it to this PNC connector, your external source. That will be your trigger source. You can use line as well as channel 1. So right now I have connected the signal to channel 1, so therefore I'm using the channel 1 as my source. Mode for now, we will leave it at auto and level, and the level is controlled by this knob as we saw earlier. The type of the trigger is edge, and if you see over here, this symbol shows that this is a rising edge. So the trigger will happen at the rising edge, and you can see that here, this is the rising edge of the waveform because the waveform is increasing. So it is crossing the trigger level, which is 0. So it is crossing 0, and it is actually the rising edge. So this is the complete trigger condition. So if I want to change the rising edge to the falling edge, for example, so I will go to slope and coupling, and here you can see that we have a rising edge. If I want to choose a falling edge, then I can click on this item, and now this is a falling edge. So you see the curve now, it's actually the falling edge, not the rising. So you see rising edge and falling edge. So you can choose whatever waveform you want. Sometimes we want to test if the probe of the oscilloscope is working properly. And to test the probe, the oscilloscope provides us with this waveform, the test waveform, which is shown over here. And it says that it is a square wave with 2 volts peak. And you can use this test point to check if the probe is working properly. So for example, if I want to see my probe is working properly, I can connect the probe to this point. And now you can see that I have a square wave. But because my voltage is 5 volts per division, so I'm going to change it to, let's say, 2 volts per division. And you can see that we have a 2 volts amplitude. And then I can zoom in on the time axis a little bit. And we see that we have 1, 2, 3, 4. We have 4 divisions. along on the time axis, and each division is 250 microseconds. So 4 division would be 4 times this, which is 1000 microsecond. 1000 microsecond is 1 millisecond, and 1 millisecond time period is actually 1 kilohertz frequency. So it's a square wave with 2 volts amplitude and 1 kilohertz signal. So if you see this, then you can be sure that your probe is working properly. Another thing is that you can remove the cap of your probe, and it will give you this tip, and you can use the tip directly to connect at different points in your circuit if you like. So you can either use this tip, or you can use the cap of the probe so that you can grab a wire or a test point where you want to measure the voltage. I would like to show two different waveforms at the same time. For this, I'm using this simple circuit with a resistor and a capacitor connected in series. The resistor is 1 kilo ohm and the capacitor is 10 microfarad. So I have 1 kilo ohm resistor and a 10 microfarad capacitor. So it's a series circuit. The same current flows in both of the components. The function generator is connected to the resistor and the capacitor over here. So the function generator is acting like our voltage source. Now I want to see the voltage of the function generator and the voltage across the capacitor. So I want to see those two voltages at the same time on the oscilloscope. Now, based on these values of 1 kilohertz and 10 microfarad, I calculated that if I use a frequency of about 16 hertz, then the delay in the voltage across the capacitor would be about 45 degrees. So we will have a 45 degrees delay. So the capacitor voltage will be 45 degrees delayed compared to the source voltage. So let's see those two, and we can measure the delay or the phase shift. We call this delay the phase shift, and we can see those two together. All right, so now I have connected channel 1 at this point, so which is the source voltage, the function generator, and I have connected a second probe, which is channel 2, at the capacitor. So I can look at the voltage, these two different points at the same time. At the moment, I have only enabled channel 1 to be displayed. If I click channel 2, and now we can see that channel 2 is also displayed. So channel 2 is the blue curve, and channel 1 is the yellow curve. Now, channel 1 is 2 volts per division, channel 2 is 1 volt per division, so it is not fair to compare the two, so therefore I will make channel 2 volts as well. So now both of the channels are 2 volts per division. So you can see that the blue curve is a little behind the yellow curve. So you see the yellow curve is the source, which is the function generator, and the blue one is the capacitor. There are a few different things. The first is that you see x-axis is the time. So let's imagine that this point is the time 0. Okay, or you can imagine that this time is 0.0. It doesn't really matter. You can choose any place on the x-axis to be time 0. So let's say if I choose that this is my time 0, then the source reaches the peak at this point. Okay, so that's time, let's say, a few milliseconds. And the capacitor reaches the peak later, after some later time. So therefore, we say the capacitor is lagging the source. So the capacitor voltage is behind the source voltage because the capacitor reaches its peak after some time, after the source has already reached its peak. So therefore, the capacitor is lagging the source. Now, how much is this lagging? So we want to calculate that. How much is this time difference between the two? And so for here, it is approximately 1 division, but a little less than 1 division. So let me zoom in on the time axis. So let's say this is the situation. Right now, my time is 2.5 milliseconds per division. The source crosses the 0 at this point, and the capacitor crosses the 0 at this point. So I have 1, 2, 3. So we have 3 divisions. 3 divisions, each division 2.5 milliseconds. So therefore, we have 7.5 milliseconds the time delay. So the capacitor voltage is 7.5 milliseconds behind behind the source. So with this information, once we know the time, then we can calculate how much would be the phase difference. And we can show that this time difference corresponds to about 45 degrees of phase difference. The other thing that we can see that the voltage across the capacitor is slightly less than the voltage of the source. So you see the voltage of the capacitor currently is less than 4 volts peak to peak. So let's measure it. So if I click measure, I will see that the source is about 10 volts peak to peak, 9.7, and the capacitor is 6.9. So the capacitor voltage is smaller than the source voltage. And this is because that this is a RC circuit and the capacitor will require some time to charge and discharge. And based on the frequency, if we do not provide enough time, the capacitor will not be able to charge completely. So therefore, the voltage across the capacitor may be less than the source voltage. So to see that, let's see what will happen if we apply a smaller frequency, right? So instead of applying 16 hertz, if I apply a smaller frequency, so let's say I do a very small frequency, and it's not. So you see, now I have applied a frequency of 1.6 hertz instead of 16 hertz. And now you can see the capacitor voltage is slightly behind the source voltage. There is not much time difference between the two. So the phase delay is almost the same. And secondly, the capacitor voltage is almost equal to the source voltage. As you can see, 10 volts on channel 1 and 9.7 on channel 2. So now we have enough time, the capacitor has enough time to completely charge and discharge. So therefore, we can see that the capacitor voltage is almost the same as the source voltage. Now let's do the opposite. So let's go back to the 16 hertz that we had before. This was the case when we had 16 hertz. So we had a 45-degree phase shift. As you can see, this is a 45 degrees phase shift. Also, I want to bring the trigger level to the center. So now you see that the zero crosses this point. So you see the phase from here, from 0 to the peak is 90 degrees, right? So you can now tell approximately that this much is 90 degrees. So this is therefore half of it, so that's about 45 degrees. Now, if I increase the frequency, so from 16 hertz, I can go to 160 hertz. And this is what we will see on 160 hertz. And now let's zoom in along the time axis. So you see that the capacitor voltage has decreased a lot. Now the capacitor voltage is only 1 volt. And because the reason is that when I increase the frequency, the time period is much smaller now. So the capacitor doesn't have enough time to actually charge and discharge. If I further increase, capacitor voltage is almost 0 now. And the frequency is 1.5 kilohertz. So you can see that the capacitor voltage is almost 0. And that's why you would sometimes hear that the capacitor is actually a short circuit for high frequency or for AC. So the capacitor is open for DC, but for high frequency, it's a short circuit. So that's why the capacitor voltage is almost 0. I hope you enjoyed today's video. If so, please do subscribe my channel. And that's it for today, and I'll see you next time. Bye for now.